The swing set is a playground classic that many of us grew up using. Although it may seem simple at first glance, there are many underlying physics concepts that allow us to have fun on the swings. In this brief video, I will talk about what can be observed when swinging, the physics concepts at play, as well as some applications of these concepts. Lastly, I will show you a sample problem and solution involving swings. Some key observations can be made right off the bat. First, we see that when the rider leans back and extends their legs forward, they are sent into a motion of low magnitude. This is how we start riding the swings. The conversion of the body's chemical energy to kinetic energy represents the first concept, energy transformation. Secondly, we can see that once the rider reaches a certain height and speed, they begin to hop out of their seat a bit. Although this is hard to see right now, a more concise clip will be used to demonstrate this later on. This hopping out will be connected to my second concept, inertia, an object's ability to resist a change in motion, as well as Newton's first law, which go hand in hand. Thirdly, the motion of swinging is a back and forth motion about an equilibrium point, which is the position when the rider is completely vertical. Assuming none of the external forces acting on the object change, the rider would swing back and forth at equal intervals. However, when external forces change, the properties of the motion also change. This back and forth movement represents my third concept, simple harmonic motion. Another important observation is that the rider can slow down their motion and come to a stop by scraping the ground. Firstly, I will talk about energy transformations, which can be defined as the conversion of energy from one form to another. When riding the swings, the rider extends their legs forward and leans back, which is done through chemical energy. This positioning of the body allows the rider to be propelled forward. The chemical energy has been turned into kinetic energy. Once the rider starts moving upward, their kinetic energy is converted to gravitational potential energy. Once they reach maximum height, all the useful energy has become potential energy and there's no more kinetic energy. As they move downwards again, the gravitational potential energy is transformed into kinetic energy. Once the rider reaches the equilibrium point where the chains are completely vertical, all the useful energy is kinetic energy and there's no longer any gravitational potential energy. Finally, on the way up in the opposite direction, the kinetic energy is once again converted into gravitational potential energy. That would conclude one cycle. At the beginning of the next cycle of motion, the rider would again extend their legs forward through chemical energy and the process would repeat again. It must be remembered that thermal energy is being produced throughout the whole motion due to friction between the chain and the structural connectors connecting it to the upper beam. Energy transformation can be found all around us. Two good examples are plants, which convert radiant energy from the sun into chemical energy to use as food, thanks to photosynthesis, and also light bulbs in our homes, which convert electrical energy into radiant energy. The second concept is inertia and Newton's first law. Someone riding a swing experiences inertia when the swing seat reaches its maximum height. At that moment, the seat has a velocity of 0 meters per second. However, the person in the seat jerks forward and slightly hops out of the seat. This scenario displays inertia, the property of matter to resist a change in motion, because although the swing seat stops moving upward, the person hops out of their seat. Newton's first law of motion states that an object will continue to move at a constant velocity or stay at rest if the net force on the object is zero. The rider hops out of the seat due to the fact that the net force is zero at max height for an instant. Theoretically, the rider would fly off their seat. However, the rider changes the net force on them by pulling on the chain of the swing, which pulls them back. A very good application of this idea is driving and seatbelts. When driving, if a driver suddenly hits the brakes, they will be sent forward due to inertia. Seatbelts help to hold back the passenger so an abrupt stop does not cause them to hit their head on the surfaces in front of them. The third concept is simple harmonic motion, or SHM for short. The cyclic motion of a swing is an example of simple harmonic motion. It is a motion that repeats itself at regular intervals about an equilibrium position. As shown by the GIF, the properties like the amplitude, period, and frequency are constant. However, in practice, this will not be the case due to friction and air resistance. In the video on the right, it can be seen that the rider stops extending their legs, which in turn causes an increase in air resistance, meaning the velocity decreases. It must be noted that a change in the external forces causes changes in the properties of SHM, so ultimately the amplitude of the motion decreases. A good application of simple harmonic motion is grandfather clocks. They have a pendulum inside them that undergoes SHM with constant amplitudes. Due to the accuracy of the motion, it can be used to pace clocks. When driving on a rainy day, we may see the motion of windshield wipers. Their constant cycle is also a simple harmonic motion. The question is as follows. Duchamp is swinging on a swing which is under simple harmonic motion. He starts swinging at a speed of 0 meters per second and a height of 1 meter above the reference level. His mass is 50 kilograms. Our givens are a mass of 50 kilograms and a height of 1 meter above the reference level. The reference level is important here because it is where the gravitational potential energy is 0 and the kinetic energy is at its max. We also know that the starting speed is 0 meters per second, meaning at the start he only has gravitational potential energy and no kinetic energy. We want to find the final speed. Due to the law of conservation of energy, we know E initial is equal to E final. Since he only has gravitational potential energy initially and only kinetic energy at the end, this can be rewritten as Eg is equal to Ek. After writing out their individual equations, we get mgh is equal to 1 half mv squared. Since mass is on both sides, we can cross it out, and after rearranging, we have v final is equal to the square root of 2gh. Plugging in the values of 9.8 meters per second squared for gravity and 1 meter for height, we get a final answer of 4 meters per second to one significant digit because 1 meter was given in one significant digit. For part B, we know that the speed in this system is not dependent on the mass, since in the analysis we cancelled out mass. From this, we know that doubling the mass of Duchamp will not change its speed.